Hi guys, in this video we're going to do a classification tree using the rpart algorithm. So if in order to follow along in this video, you're going to need to install packages rpart. So go ahead and do that. I already have done this. It may ask you to select a mirror, so in that case select a mirror that's close to you. For example, if you're in China, pick something in China. If you're in the US, pick something in the US. Okay. You'll also need to install, so hit enter here and go through the installation process. You'll also need to install a package called rpart.plot. Okay, so go ahead and do that. Probably won't ask you for a mirror there. Okay, once you've installed both these packages successfully, require them. So basically load their functionalities into your current environment. Okay, as I've done here. Okay, and so now we can focus a little bit on the data set that we're going to talk about. We're going to use the iris data set, which you should all have already preloaded in your R environment. So let's just pull it up. So this has to do with the species and some other attributes of flowers, I'm guessing. Okay, so there's 150 examples and 5 features. You can see that 4 of the features are numerical and 1 is a categorical, nominal, or as it's coded here, factor feature variable. Okay, so this happens to be the feature that we want to predict, right? It's categorical. It takes on 3 levels: setosa, versicolor, and we're not seeing the third one here, virginica. Let's quickly take a glance at that with using table. In virginica, as you can see, it's quite a balanced data set here. We have 50 examples of each of these species. That's very nice. Okay, so we want to be able to predict the species of a flower using some mixture of the other attributes of that flower. Okay, so since our target is a categorical feature or categorical variable, we're in the general techniques of supervised learning, specifically classification. Supervised learning. Okay, so we have many choices here: k nearest neighbors, naive Bayes. We're going to use classification trees here. Okay, so before we jump into that, let us do a little pre-processing of the data. Okay, so if we looked at this data set, you would notice that it is in somewhat ordered form. Okay, so it seems like all the species are kind of listed: setosa first, then maybe versicolor, then virginica. That is something you should always watch out for. You don't want to feed data into an algorithm that's ordered if there isn't some kind of special order that you want to consider. Okay, so in other words, it's like playing cards. You should shuffle the deck before you start playing. So we're going to shuffle the rows, the examples in this data set before we do anything further. Okay, so in order to do this, we're going to, if you want to get the same results as me, follow along. We're going to set a seed, and this will guarantee that the randomization that we do here will be the same, that you'll get the same results as me, in other words. Okay, I'm going to create a bunch of random numbers between 0 and 1, so that's what this is doing. How many? Well, as many as rows I have in my data set, so I'll tell it to make that many. Okay, so actually there's 150 rows, so I just created 150 uniformly distributed random variables. Okay, I'm going to use these simply to reorder my iris data set, and I'm going to call the new iris data set iris R. And the little R is to distinguish it and maybe to remind me that this is a shuffled or randomized data set. Okay, Now, what is iris R? Well, it's just plain old iris except reordered. So the order depends on the order of the random numbers, and these 3 lines of code will give me some assurance that I'm dealing with a shuffled deck of cards, a shuffled data set before I begin doing any kind of statistical learning. Okay? Now we can actually begin using the rpart package to learn a classification tree. Okay? Okay, so the rpart algorithm works similar to the lm function in R. If you recall, the lm function requires you to input a formula. So how do we do this? Well, it's basically of the form target tilde predictors. Okay, so our target here, if we go back to the structure of iris, we'll see that our target was species and our predictors were these guys. Okay, so rpart target species, make sure you get all the capitalizations correct, tilde. Now we can spell out all the predictors that we want the algorithm to consider, separated by plus signs. And as you can see, even with this tiny little example that we're doing here, this could become a little cumbersome. And in fact, I'm going to show you a better way. If you want all the features considered, you can simply type dot or period. Okay, this will consider all the other features as possible predictors in the model. Okay, comma. Next thing we should tell it is which data set that this data comes from. Well, let's do iris R. Okay, and actually let's not look at the entire data set. Let's look at the first 100. And the reason why I'm doing that is because I want to leave the last 50, because there's 150, for testing purposes. So you can think of what I've defined here as my training data set. So the first 100 rows or examples after I shuffled, I'm setting aside for training purposes, and the last 50 I'm going to use for testing purposes to evaluate my model. Okay? Okay, and finally, we should explicitly make the method clear to rpart by telling it that our target is a categorical feature, so we want it to create a classification tree. So if we make this argument clear, we leave out any guesswork. Okay, so we should probably give a name to this model. Let's call it M3 or M3. Okay, let's enter. No errors. Things look like they went well. Let's look at M3, and we get a little output here. It's quite useful. You see we have 100 examples we're starting with. Here's a little legend. Okay, so node number, which feature it was split on, how many observations, how many misclassifications, what's the prediction if you were to stop there. Asterisk denotes a terminal node, or what I call a leaf node. So let's take a look at, so this is the legend here. Here's the results of our output. So look, this is a leaf, leaf, leaf. So this tree has 3 leaves. Here's the root, okay, and everything else is an interior. Okay, we can actually draw this if we like. So let's go ahead and try to draw this. So let's make some blank space here. Okay, so we're going to start our tree by splitting, so it's somewhat square, just to keep my convention straight, on petal length. So I'm getting that from here. So if the petal length is less than 2.6, then we're going this direction, and this is a terminal node, so it's a leaf. So let me make my leaves round, and the prediction here is setosa. Okay. If my petal length is greater than 2.6, so I'm here, so greater than or equal to 2.6, I'm getting that from here. Then it's not a terminal node, so we're going to be splitting on another feature. So let me make it an interior node. If I were to stop here, the prediction would be versicolor. But this continues, and we're going to split on petal width. So let me abbreviate it like that. And petal width, if it's less than 1.65 centimeters perhaps, then we're going to be in this node. It's a terminal node. The prediction is versicolor. So let me abbreviate. And if the petal width, is greater than or equal to 1.65, we're going to go the opposite direction. So notice these branches are all either this way or that way. They're binary splits. So I'm here in the last node here. It's a terminal node. So there's going to be a prediction we should pay attention to. Prediction is virginica. So we can see this tree, virginica. This tree has one root, of course, but 3 leaves, okay, and 1 interior node. So these are all nodes. Here's the decision. Here are the branches, right? Okay. The cool thing about the rpart package is we're going to be able to kind of automatically generate a diagram. It might not be as pretty as this one, but it'll be a lot less work. Okay, so that's basically the interpretation of what we learned from the output of our classification tree algorithm using rpart. Okay, so let's actually plot that. So rpart.plot will do this for us. So we called it M3. Our model is M3. If we were to just hit enter here, we'd get a little kind of tree. It's not the prettiest tree, but you can see it's somewhat telling us the same information that we were looking at here and that I just drew before. We can tweak it a bit, and here are some options that I like. So type 3, extra information 101. Let's tell it to show fallen leaves. Okay, and if we do this, we get something that looks a little better. See, it leaves out the root and interior nodes. I mean, it doesn't leave them out, it just doesn't draw them. So you can, this would be petal length. So let me do petal length. This would be petal width. Okay. Besides that, it's exactly like the tree that we just drew. Except instead of writing the petal length up here, you see it makes it clear here, and you just should assume that this is also petal length greater than or equal to 2.6. So this split has to do with petal length. Okay, so petal length turned out to be the most predictive feature of the 4 features that we gave the algorithm to choose from. Okay. And here are the predictions, and we see some percentage here. So the percentage is telling us what percent of the total 100 training examples ended up in each leaf. So 34, 37, 29. That should all add up to 100%. Okay. We see also the raw numbers here. So see, this is actually a very pure leaf. There were 34 setosas correctly predicted here, 0 of the other types. This leaf is also pure. There were 29 virginicas actually ended up in this leaf, and 0 of the other species. And here there was just 2 errors. Okay, and I think if we look at the summary output, we might get some kind of indication of that. All right, so you see there's a lot of output here. Okay, so you can delve deeper into this. All right, but what I want to do actually is, now that we've drawn this, we've visualized it, we can actually make predictions on our own. But let's use the training data that I left aside, the 50 rows at the end of the data that I left aside to see how well this model generalizes to a new data set, to an independent bunch of examples. So to do this, first I need to make a prediction. Okay, so I'm going to predict using M3, and I'm going to predict from iris R, but this time from row 101 to 150. Okay, so that's my test data, and the type of output I want is class. I believe that should do it. Let's go home. Let's call these, we're going to get a vector here, so let's call that P3. Okay, so we have our predictions. So we have our predictions stored in P3. Now we'd like to make a confusion matrix to see how well our model did. So we have the actual species of the 50 test examples. So let's pull those up. Let's put those on the horizontal axis. So look, confusion matrix, right? So we're going to put the actuals here and the predicteds here, and then see how many corrects we had, how many errors we had. Okay, so first I'm putting on the horizontal axis the actuals. Okay, sorry, on the vertical axis. So this guy, I'm going to put the actuals. So I place that first with the table command. So I'm saying row examples 101 to 150 only give me the species. That was column 5 in our data set, and for the predictions, I just simply can call P3 because that's what I named them. It might not be a bad idea to call these predicted, so you could put that in there as well. So predicted. So here we go. Okay, so it correctly predicted 16 setosas to be setosa. It correctly predicted 13 versicolors to actually be versicolor. There were 17 virginicas that it correctly predicted to be virginica. So these are the correct predictions. So of the 50, there are 16 plus 13 plus 17. So is that 30, 46 correct? So 46 over 50. You can think of that as somewhat of a performance measure, okay, of how well this model predicted generalized to new data. Okay, let's talk about the errors though. Let's focus on one at a time. So 0, 0, 0, 0, those cells are correct. They had no errors. But what does this 2 mean? So there were 2 versicolor species flowers that the model, using rpart and the classification tree, actually predicted them to be virginica. So it made 2 errors of that type. Okay. Then there's a 2 down here. There were 2 virginica flowers or species that the model predicted to be versicolor, and that's what that 2 means. Okay, so error, error. These guys are the correct. Were correct. Okay, so not bad, not bad. Okay, if you watch the other video where I made a classification tree with the C5.0 algorithm, it'd be interesting now to compare the 2 and to see kind of which one did a better job. So let's do that. So I might still have that. So I might think I call that P1. Yeah, that rings a bell. So to see how I got this P1, you need to watch the other video I've done on classification trees using C5.0. It's a different algorithm that uses slightly different methodology. Okay, so you see that the results are slightly different. The diagonal here, 16, 16, that looks the same, but you see already here the numbers change. So here, it's very close. So this guy was, so actually, you know what I could do to even make this clearer? Since now we're comparing things, let me, P3 was what we just did with rpart, so let me call this rpart predicted, and then let me call the P1 predictions. These were from C 5.0, which was a different video, okay? And we're looking at the confusion matrix for both of these. So you see that they both did a pretty decent job. This one had, C 5.0 had only 3 errors, where rpart had 4 errors out of 50. That's pretty good. Okay, so both of these fit to the new data, the independent data set, test data quite well. Okay, so it's a toss-up in this example as to which would be better. But sometimes it's nice to try different algorithms that have slightly different methodologies to see which does a better job at making predictions. Okay, and here I presented rpart. In the previous video, I presented C 5.0. Both of them built classification trees for us using the same exact data set. So we get to see them side by side. There are also other algorithms out there, but these are two kind of popular ones that I've used myself in the past. So I hope this series of videos were helpful on classification trees. Make sure to watch the other algorithms that I've done, KNN, regression, and so forth on the machine learning playlist. Till next time, have a great day.